if you have a binary number, like so, and we want to take the number, let's start with a simple one, 1101. What you're going to do is look at each one of these going through and really writing it either direction, because you can recognize that it's 4 bits in, and it's always 2 to the n minus 1. Is everyone comfortable with that notation? So if this is the 4th bit, it's 2 to the 3rd. So that is 1 times 2 to the 3rd. And then we can just add them together. This is 1 times what? Yeah, 2 to the 2nd. 0 times, we don't really care. And then the next one is plus 1. That's it, right? Because it's the last one. We add that up together, and you can figure out the number, right? So this is equal to, what's 2 to the 3rd? Plus naught, plus 1. So we have 13. That's binary to decimal conversion. And that's really kind of the easy way of doing it. Your rules can actually end up being the same thing. You can extrapolate this to any base. So you could have, the book uses this example, 734 base 8. Ours works, right, because our base 10, and it's just 2 to the 10 times each of those digits. Nothing fancy, it extrapolates out. We're going to worry primarily about binary. Now, binary does this really weird thing where, let me just know. You can have decimals, right? So for number theory in general, when you have a decimal point, we call it decimal point because we have digits and we're in the decimal system. Binary, I'll have to think for a second what it is, but the generic term is the radix point. It's when you switch from whole numbers to fractional numbers. So for binary, if I add 0.1, what is the value of that 1 there? Because we know it's not 1/10, right? Yeah, and what's another way of writing that one? Yeah. Or 1/2. And then as you start adding them, they become, right, that's 1/2, 1/4, 1/8, right? So going up, it's doubling. Going down, it's cutting it in half. And your conversions work exactly the same. You just start adding those fractional values as you go on off to infinity. The book has like all sorts of examples of this that are probably worth going over. I will probably throw one of these questions on the exam for fun. So look at the examples. It'll probably be on your homework. Before I forget, I did post homework for last Mondays, but I'm gonna, and normally homework is due 2 sessions after. I'm gonna extend this one, so Monday's homework and Wednesday's homework will be due next week sometime. The Canvas will have the due dates. Is anybody not familiar with Canvas? Okay, we're good. Okay, let's see, where are we going? Now we need to be able to go the other direction. Well, maybe we'll do a more complex example that you guys can get your teeth into. So go ahead and convert for me on your own to start this number, 1, 0, 1, 0, 0, 1, 0, base 2. Right, remember base 2? I had a few people puzzling through still. I'll just give it another 30 seconds and then we'll jump on. Okay. Yes, who has a value? 210. Did anybody not get to 210? Good, excellent, yeah. Again, it's just figuring out what that highest value is, 2 to the n minus 1, right? You can also start adding from the other direction and count up, but it is helpful to identify what that largest value is. And that, because that gives you a ballpark, right? It will never be more than double whatever your first one is. But we also need to go the other direction, right? You know you have a value, and we need to create binary out of it. Now this one, there's a couple different ways to do it. And if I'm doing something like, once you're experienced at it, you can do something like, okay, I need 164. And you can do mental gymnastics pretty quickly once you're accustomed to it, to be like, I know that one of the binary bits is worth 128, and then you can figure out what the next largest one is that you can get closer, and you just slowly, incrementally get closer to it. Or you can do what this book recommends. Are we good if I erase? I have a confession, I have never in my life done it this way until right now, so let's do it. So let's say I have 217 as a number. I like to do things the hard way for some reason. I blame my undergraduate research advisor. So, 217. What you want to do is just start dividing by 2 a lot. So if I have 217 divided by 2, what is it ignoring the remainder? 108. So 217 by 2 is equal to 108 with a remainder 1. Let's bring that 108 down. What is that equal to? Remainder? Not. Yep. Divided by 2. 54, drop it down.
27.
Remainder?
0.
Not. Sorry, I watch a lot of British television, so I say not for 0. There's a reason for my... But on 27 by 2.
13.
13.
6.
I should do this more often, but 6. 3. 6 divided by 2, sorry. 3, no remainder. 3. We end up with 1 of a remainder 1, and then 0, remainder 1. Okay, so now, fun. All we have to do is worry about the remainders. And in reverse order, we go 1, 1, 0, 1, 1, 0, 0, 1. Right? And that just so happens to be, unless I did it wrong, 217.
I got a question.
Yeah.
I got a question going back to converting from binary to base 10 or
Yeah, decimal.
decimal.
Base 10 is also true, yeah.
So usually what I do, I don't know if there's a quicker way to do it, but I like above the places, I put like, okay, the first spot is like my ones position, second spot is 2, 4, 8, 16. And I do that, like I write it above it, and then like on my calculator, I just add up all the ones with the 1 below it. Is there a quicker way, or is that like a good way to do it?
No, that is a perfectly fine way to do it.
Okay.
So what he's saying is he'll start from here, right? And you're going to start with the way I started. 1, 2, 4, 6. Wow. 8, 16, 32, 64, and 128. And then he'll draw it like this. And everywhere there's a 1, you just add that value. So it's 128 plus 64 plus 16 plus 8 plus 1. That is another completely, totally fine way of doing it.
Yeah, because I kind of missed the first part of the class, but did you show a way of doing it other than that?
Just identify. It's very similar. It's just identifying the 2 to the n minus 1 powers, which is exactly what that is,
Okay.
and then just writing it out explicitly as a multiplication.
Oh, so like 1, 2, 3,
yeah.
4, 5.
So that's kind of the shorthand way of doing it. So here we would write it 1 times 2 to the n minus 1, right? Whatever we're at for each slot, plus 1 times 2 to the n minus 2, and so on and so forth. And then if you have a 0, then it's plus 0 times 2 to the n minus 3. And that just becomes the return. So this is probably the quicker, cleaner way to do it. That is the mathematically rigorous way to do it. There are examples in here that are just all about the decimals, and I'm not going to go through the example. Maybe have a look at the decimal, but literally all you're doing is instead of the divide by 2 when you're starting to calculate these, it flips to multiply by 2 because you're dividing by right, and so on and so forth. And the next step would be 1 by 1 to the 4th, because this keeps dividing. The fractionals, they're irritating. Computers don't know about fractions. They have no clue. Because it's either on or off. It has no idea about numbers. And so if you have a decimal point, you have to tell the computer that's a decimal point, essentially. Microprocessors, more than FPGAs, this is mostly an FPGA system. Microprocessors handle what we call floating point, which I'll talk about probably in a little bit, which is where that decimal kind of moves around. But generally we use fixed point for FPGA, which is there are n bits before the decimal and n bits after the decimal, and they are what they are.
So I got another question. So you were, with this method of going from like base 10 to binary, you said you've never done it this way. What was the way that you've done it?
The way I do it is literally find the biggest number that I can think of. So if like I have 217, right? I know that I have a power of 128, and the next power of that is 256.
Oh, so that was too big.
So then I know that it's one less than 256, and then it's just a matter of figuring out what the next largest one that I can have. So if I know I have 128, then I just ask myself, what's the next step down from 128, right? So if we're looking at 64, I ask myself, can I add 64 to it? Yes, I can. So I do it. Then I ask myself, after that, can I add another 32? No, I can't, so I won't do that. So then I start just going through 1, I can't add a 32, and so on. So this is the reverse method of it versus counting up, counting down. That's all it is.
But with this method that we just got, you just got to make sure that you flip it.
Yeah.
Go from the bottom.
Your bottom up.
Why is that? Why, like mathematically, why do you have to go from the bottom to the top? Because like in my mind, I would think you'd go from the top to the bottom.
I would think so too. I don't want to go through the derivation. I don't even know if they do a good job of it in this book of doing that derivation. But it comes out of the simplification of the powers rule.
Oh, okay.
Well, binary follows the same order as decimal, so that doesn't flip either. It's just that you are solving for the largest digit first, and that largest digit, the 7, when you do that first division, that remainder is telling you about this 7.
Oh, right.
Which is the smallest value.
Right.
Okay, let me make sure I don't miss any other useful examples. And we're going to move on to something else, which we call hexadecimal. So hexadecimal is a very commonly used, let's call it a compromise between binary and decimal. So hex, as we generally reference it, you'll usually call it hex, hex code, etc. It doesn't just use 0 through 9 as its numbers. It includes A through F. So if you'll see this, the most common place you'll have seen this just in your regular life is color codes. What color is that?
White.
I don't remember. It's either white or black.
There's
I don't remember which.
It's supposed to be 6 digits in color code. RGB 2.
Yeah, well, there are different standards. I come from an era of HTML when they used 4.
HTML now they use 6.
Everything's gotten bigger and bigger. In fact, in the early days, they used 2. So if you go back and look at a Super Nintendo, it's 2. They don't even use all 8 of those bits either. Anyways, so what hexadecimal is then, when it adds the A through F, is it now has each digit an A. So in binary, each one is 1 or 0 is 1 bit. In hexadecimal, you have this nice thing where each one of these is worth 4 bits. That's an A. So what that means is it's both human readable. I mean, you can have weird stuff, right? That's a number, 6AF. But what's nice about that is it's both descriptive to us and easy to convert into binary. So the book provides you with a pretty little table of what 0 through F mean, and that's their recommendation. You can always just write it out, right? Actually, I have a question. Do you guys know what truth tables are? Does anyone not know? Okay, so this idea of a truth table, and this is a very simplistic version of it, where if you get lost and confused, and I'm mean and I don't put it on exam, you'll have n bits, so, and we can call them A, B, C, and D, and we can start just counting up in binary. And so on and so forth, right? This is how we count in binary. Anyone confused by binary counting? Okay, and then, as this counts up, you're just going 1, 2, 3, 4, 5. Now, this is not a true truth table. We'll get into those more, so don't confuse this exact thing for truth table, but this is the format that these tables take. And you know that 0, 0, 0 is 1, and 0, 1, 0, 0 is 5. And that's all that this is showing you, is a table to look up what the value is until you get down to 1, 1, 1, 1, all the way counting up, which is F. And you can fill in the rest of this pretty quickly. So if you ever get lost and confused which is which, it's easy. In fact, it's really easy to start at like 8, right? Because 8 is just going to be And most of these other ones are kind of intuitive. This one you get into letters that people usually get confused. And then you can do 8, 9A, because that's how we count. We don't have 10, right? Because 10 is now 2 digits, so we switch to 8. And so if you wanted to start at 8, you just start at 8 and count up from there.
All right, quick question. Does the truth table have a 0 or does it start at 1?
It starts at 0.
Okay.
So, sorry. This is MATLAB sneaking through, and I would like to apologize, and this is why we're dropping it from the program. Thank you for catching that. This is part of the reason we're dropping MATLAB, is because it gets you in the habit of being one indexed, and it's not. It's the only thing in the world that still does that. Okay, so let's look at a number. And we're going to call it a nice big long number. 101. That's really just mean. This book really likes decimals. I think they're tedious and boring, so I'm just going to call the decimal. Go ahead and convert this to hex. While you guys do that, I'm going to take my photo roll that I need to for COVID requirements. Yes, 5B4. Did anyone not get that? Any questions? You look a little confused?
Higher, I think I got it, where it's like, it's the splitter, it's kind of just splitting up into the 4 parts.
Yeah. And when you start grouping them, start down here at the least significant bits. And if for some reason you decide you like decimals and you're doing it, you start with your most significant. Oh, that's terminology I forgot. Least significant bit, most significant bit. Least significant, meaning it's going to contribute the smallest amount to the sum. Most significant bit contributes the largest number. LSB, MSB. when you start grouping, start at the LSB, because you don't know if you're going to end up in this situation where there's a floating 0 here for that bit. Because like decimal, we don't write a million zeros in front of it unless you're in binary and you're doing, what's it called, a fixed point, right? If you have a 128-bit number, you need to define zeros for all of those. This is one of those fun examples in VHDL, which you guys will learn in this class, versus Verilog, which is what I learned on. Verilog doesn't care. It's what we call loosely typed, meaning Verilog, you can just start throwing numbers or letters or anything you want into a bit, and it will just make it fit as close as it can. VHDL, like C, wants you to be very explicit in the number of digits. Okay. Let's go the other direction now and convert this to binary. All right, where do you want to start? So this is actually kind of fun. Doesn't matter, 5 or D. You can start either direction in this, because even though 5 is going to give you starting with a 0, it's not wrong to put a 0 in the leading 0, right? You're not going to get it wrong. So what is 5?
0, 1, 0.
Yep, C.
1, 1, 0, 0.
1
0.
and D.
1, 1, 0, 1.
Smash that together, you got your binary number. Now this is obviously a very large decimal number as well, right? You have 2 to the 16 as your largest, well, 2 to the 16 minus 1 is your largest number. 5C1D is kind of nice to look at when you're writing code and such. You will run into hex a lot, but it is easy to convert to binary, which is what computers like. Any questions on hex? Okay, so now we run into the next problem. A computer only knows ones and zeros. It doesn't know a negative number. How do we do negative 5C1D? Well, the only thing we can do, we add another bit. If it's 0, it's positive. If it's 1, it's negative. So you just define one bit to be positive and negative. This causes a weird issue, though. What is the difference knowing that 1, this is the negative number, and this number? What's the difference between those two numbers? Nothing. So you have a weird positive 0 and a negative 0. So we do what's called 2's complement, which is a rather obnoxious way of dealing with what I consider to be a fairly minor issue. But they do it all the time, and so this is what it was. So instead of saying this is a negative 0, or negative, right? Instead, your MSB, your most significant bit, is negatively weighted. So if I put a 1 here, that means this number is no longer negative 0. It is instead negative 2 to the n minus 1. In this case, 2 to the 3. And then I count up from there. So if I have a 2's complement number, and I want it to be negative 1, how do I do it? So we'll do it simple. I have 3 digits. And I want this to equal negative 1. What do I need to do first off for it to be negative at all?
1 is the most significant bit.
Yep. And so if I had 1, 0, 0, what am I at?
Negative 0.
No, because this is the MSB. So this weight is 2 to the 2, and it's negative. So what is my number currently if it's 1, 0, 0? Negative 4. Okay, but I need to get to negative 1, so what's the next thing that I do?
You add the other digits.
Yep, I add this one and that one, right? Because this is minus 4 plus 2 plus 1. So in using the other example that we did before, you can just write the weights. And add them together. Right, so I have minus 16 plus 4 plus 2. So that is negative 10.
Okay.
Everyone's good?
If you ever just need an 8 or something, you just add 0 before it.
Yep, yeah. If you wanted 8, you would just do 0, 1, 0, 0, 0.
Okay.
Okay, so this is actually a pretty good exercise to have everyone do to make sure you get it and you don't run into unknown snags. Just to keep in the habit of examples, please convert negative 109 to 8 bits two's complement. I don't want to write it down. Oh, this would be an 8-bit two's complement number. right, do we have a number? 100100011. Now, most of you, actually, did any of you attempt the division method? Yeah, see, no one likes it. There is a possibility of using the division method on this one, though. The first step in it is, if you have a negative, is you just write down the 1 for the negative, and then you add the equivalent of the MSB to the negative number. The MSB is 128. So you take 128 plus 109, and that is equal to 19. And then you can go through that division process, which is going to end up being, by 2 is 9, 4, 2, 0. And then you're going to do, right, and we have remainders on this stage and that stage, 19 in there, and then we have a remainder down here, actually, if I screwed. No, sorry, I have to puzzle out what I did wrong. 19 divided by 2, this is where the remainders are. I was shifted by 1. A remainder. There's a 1 here. These are the numbers, and again, we're going in reverse order. So we have a one, two, three, 4, 5, 6, 7, 8 bits. We know we get a 1 there. Where does this 1 go? Which side of the 8 bits? All the way over here. So we now have a 1, 1, 0, 0, 1. And we know that there's zeros in the rest of that, because if we kept dividing 0 by 2, we just get more zeros. 0. So that's how you do the division one, is you just add the MSB to whatever the negative number is. Yes?
So how did the computer recognize that this number, 10010011, is negative 109 instead of 137?
So it's by typing. So you tell the computer what type of number it's dealing with. That's how you tell it. That's all it is. The computer, there's no magic there that it can solve. So you'll have types, numeric types in all languages. If you learn C or if you learn MATLAB, right, you'll have ints and what are the other ones that they call it? I don't know C very well, if I'm perfectly honest.
It doesn't have any negatives.
But yeah, the uints. Longs floats. Yeah, there you go. Thank you for filling in for my blanked mind. Okay, onwards. There's this. This book has quite a few examples that you can follow through. Actually, that I'm not going to step through all of because we don't have infinite time. Actually, I'm going to ask. Does anybody want to go through another example of the 2's complement in class? If anybody would think it would help, raise your hand. You do think? You got two? You do think? Okay, we're going to do a little more of a complex one. Start with a fresh board. And we're going to go ahead and convert this isn't even in the book, so I could do this wrong, but we'll find out. We're going to do 721 into a 12-bit 2's complement.
just got a question. So is there like, there's hexadecimal and there's binary. Is there anything else?
Yes. So you can have literally any base if you want. There are base 7 numbers. Historically, people have used base 7 numbers for a couple of different reasons. One of it makes it very confusing if you're trying to write a code and people are like, if you're trying cryptography and you start using a base 7 number, it can get very confusing for people very quickly if they're trying to know what you've done. I've seen at the National Lab in really archaic code of base 12, which I still to this day don't know why they did it. But generally speaking, the binary, hex, and decimal are everything that you'll deal with.
So that's base 10, base 2, and base
16.
hexes and 16.
Yeah. Yeah, because it has 16 bits per.
Yeah, hexadecimal, it's 6 plus 10. Hex, yes.
Hex is a weird one. Hex came into my knowledge, not even through my digital courses, it came into my usage through actual industry applications when I was picking up and fixing other people's design. I was like, what are they doing? It was very confusing to come at it from an industry rather than an academic standpoint. All right, what is the first thing that we do? We write that -1. Do we want to walk through this, slowly build it up, or do we want to do the division route? No preferences? Did anyone do it the division way?
I do.
Should we try and find out if it works? Again, this is not my usual. So if we know it's a negative, what is our MSB value going to be?
148.
Are we confident in that? Because I'm not even going to double check you. Okay, and then we add that to the -721, which gives us what value? Sorry, 1,000 what?
327.
327. And then we're going to start dividing, right? So if we divide that by 2, we're obviously going to get a remainder. And rather than doing this down, I'm just going to start filling in because we know that we're going in reverse order, right? So where is this remainder going to end up? All the way at the end. So we've got a 1. What is the value without the remainder?
663.
663. That's going to give us a remainder, it looks like. Those that didn't do it the division way, are we looking good so far? All right, give me another division.
331 with the remainder.
With the remainder. Next one.
165.
165. That sounds like it has a remainder in it. Next up.
2.
We got a remainder here.
No. Yes. No. 82 billion.
I've lost track of those. Are we doing the remainder for this one, or are we doing the remainder for here?
Remainder 482.
For remainder for the 82. Got it. Next number.
41.
I have a remainder.
No.
Yes.
Next one.
20.
Without a remainder.
Yes.
And the next one's going to be 10 with no remainder.
5. With the 2.
With the remainder.
No.
No.
1. With.
Okay, so doing the division route, it looks like we got ourselves a 1101. Does that number look right to those that you did it the other way? Excellent. Wow, it works. There are examples in the book that can help you puzzle through it that you can try out. And I'm sure there are hundreds of examples online that will walk you through. 11. Okay, so we got what, 20 minutes? We can stare at that for a second so that if anybody's confused, they can puzzle through what happened there. If you have any questions, just yell out. I want to make sure I didn't miss anything. Yeah, this book really likes the decimals. I don't think I'm going to do the decimals on the exams. There are decimals in the homework to be done, so you'll want to look in on how to do that and follow through. They're not that difficult. Yeah. So there's a potential issue that when you do these designs, that if you had something like negative 727 and you only allocated 11 bits or 10 bits, you're going to have overflow. So those bits are going to go off into nowhere land. And depending on your case, depending how you've designed the system that this is feeding into, you don't necessarily know if you're losing the leading bits or the trailing bits. And the leading trailing can be a little bit of confusing terminology because different systems will transmit the MSB first and others will transmit the LSB, right? Most significant bit, least significant bit. And a lot of times as a designer, it's your job to decide which to transmit first. And other times you'll go pick up at like an ADC that you need to control with serial communication, for example. ADC is analog to digital converter. It's how you interface a digital system with the real world, and it will have what's called a serial interface, meaning the digits will come out one at a time and you'll slowly read them in. And when you do that, you have to know, did it send the most significant bit first or the least significant bit? And that's where the data sheets come in. You'll read through, verify that you're not crazy, and do it. This is one of the most common errors that I'll see new students make, is confusing the order of MSBs and LSBs in the transmission, or even in where the register. So the register is what a computer thinks is those numbers. So that would go into a 12-bit register. It's holding on to those 12 bits, they're registered there, and you need to know which location they're at. That, my friends, is chapter 2. Let me look. We've got a little bit of extra time, and let me look at the time, actually. We've got 15. I have a clock over here, but it's broken. Maybe we should do one binary example, binary decimal example, since there is some of the homework. Where's a good one? Sure, this one's fun. This is the final example in the chapter that we can walk through. It's okay, so we're going to convert a 2's complement number.
Good question.
Yes.
When you say 2's complement number, does that mean it's with the positive or negative in front?
So 2's complement is specifically the leading number, the most significant bit, is negatively weighted.
So for the 2's complement, it's always negative.
Yes. But if I put a 0 here, having a negative 0 means nothing. So the number itself can be positive.
Okay.
So if I have this number, and I say it's 2's complement, that's 0, right? So the negative is negative times 2 to the 3, because it's n minus 1. which is 8. So negative 8, but it's times 0 because that's the value. And then here we just have that value by itself.
What two's complement was referring to.
Sorry.
Yeah, you're good.
Yeah. And so you can also have just signed, which means that this is only a negative. It doesn't have that weight to it. So there's signed numbers, and then there's 2's complement. Good question. Okay, so we're going to have a number. Oh, this is a really lame example. Give me a second. This is a good way of doing it. Okay, let's convert negative 12.38 to an 8-bit 2's complement. So this one, again, is a little bit weird. So let's go through the process together. The first thing that you do is you can fit this whole number into a 2 to the 3 pretty comfortably. I'm a little confused why they wanted to do that. Because it wants to get rid of, let's see, how are they doing this? Well, you could do 2 to the 4 to fit it, but I'm also just trying to shift out the decimals so that I don't have to worry about those as much. And so if I multiply it by 2 to the 3, then I end up with like I don't think I'm going to ever have you guys do one of these conversions because these are meaningless if I'm perfectly honest. Like on an exam. I won't do these negatives, I don't think, on an exam because they're tedious and you will never do this in real life. And then if I round out that negative 4, which is going to round out, get rid of it by having a remainder. Let's scratch this, guys. I'm not going to have you do this on an exam. I might even rewrite the homework to just ignore the negatives. Let me look at the homework questions real quick to see what you actually need to know. Because this stuff is, I don't do it, right? A lot of my experience is industry. And so when I see this academic sometimes stuff, I get kind of annoyed with it because I don't know why you're doing it. For the following binaries to decimal. So you guys, I feel pretty confident can do a binary to decimal, especially if it's not 2's complement, right? Even if there's fractions, because it's just 1/2, 1/4, etc. Down past the decimals. Yeah, I'll look at this. The homework is assigned out, and then I'll just send a supplement to minor tweaks to the homework, and we won't worry about the 2's complement negative stuff. I don't think it adds much to the class, and I would rather save that time and effort and learn VHDL better, because historically, if I'm talking to my 3610 students, they don't feel confident in VHDL. So if I can get ahead and get better VHDL education in this, I will be happier with that.
So you said you're going to change the homework?
I'm going to change the homework.
So don't do it yet.
Don't do today's homework yet. You can do last time's just fine. And if you do the homework as is, if you start it and you're like, oh, this is easy, go for it. You're not going to get it wrong based on the change, because the changes are going to be like, there's a question. Actually, you know what? This is like question 9, I think, might be the only one I've changed. It says, convert the following decimal numbers to 8-bit 2's complement. Assume 4 fractional bits. I might just drop 9, or I might just say drop the decimals. we'll see, right, it's going to be that simple. There'll be some minor changes to it. That's probably time to go. I'm going to end a little bit early. If you guys have questions and need review, then we'll have 10 minutes that I can chill out here to help you guys if anybody needs help.
Can I get a picture of the homework problem?
Oh, absolutely. You know what? Actually, you can just take the sheet if you like.
I would like.
Bond. Sorry. Yeah, so Fawn Brown wrote the book, and we're having issues with it getting online. That's the chapter. You can go ahead and read it. I don't think I have too many weird notes or anything on it. Like, this doesn't apply to you. Not that you'll be able to read it.
Yeah, cool. Is this just chapter? This is just chapter.
That's just chapter 2.
Chapter
This will be chapter 3. I don't have chapter 1. Chapter
That's not the book.
No. This is the 3610 book. I will reach out and send out an announcement for those that don't have the book. I will figure that out. I don't know yet. Okay.
Chapter 1.
Oh, your book?
Oh, yeah. 970. 319. 1320. 70.
Oh, so this would be so this would be last time's homework.
So what is that's where we're starting. Yeah, cool.
Yeah, if you need any, I got